I will discuss today anomalies, mostly in matter. But please, in matter. But before starting, I want to clarify two issues from the last session. First is something I say wrong, now without any palliativos. So it was, if you remember, when I was discussing the Landau-Fermi liquid as a fixed point of the renormalization group, I tried to tell you that there were Landau-Fermi liquid, that all four Fermi interactions were irrelevant at the tree level, apart from some specific kinematic channels, remember? So there were F forward, backward, and what we call BCS channels that became marginal because of the kinematics of the Fermi surface, right? So I told you that these two forward and backward were, when you go to the one loop, were marginally irrelevant, and this one was marginally relevant if the interaction was attractive, something we know, the BCS. But these are not marginally irrelevant, they are marginal to all orders. And that's why, of course, we have this zero sound and the first sound and all these excitations in the Fermi liquid. Okay, so that's the first. Some of you pointed this out to me after the lesson, and of course, it's completely right. Okay, that's the first. And the second thing is a clarification. This wasn't anything wrong. I think it was right that there was some misunderstanding concerning the chirality of the standard model. I think it was you who mentioned. And in this case, it was just a misunderstanding, meaning the standard model indeed is chiral in the sense that is this SU3 cross SU2 cross U1. These two come is electroweak interactions, and this is strong interactions, quarks and so on. And the multiplets in the standard model come as chiral particles. It's true that you say, okay, well, I have the electron left, and it's neutrino, and then E right, and neutrino right. So it is true that is organized in chiral multiplets. There is a reason for it, is that this SU2 breaks parity, and then parity exchanges chirality. So in any case, this was made consistent out of Weyl fermions. The question is that Weyl fermions do not exist in nature. What I mean is that there are no fermions that are candidates to be Weyl. Okay, so yes, the standard model is chiral, but there are no massless fermions in nature, okay? Any questions about that? This is important, and I thank you for pointing this out to me, because indeed, if the standard model was organized into left-right particles, then there wouldn't be any anomalies. So any of the anomalies that I'm discussing today. So the question now, of course, arises, and now I'm coming to my point, is if there are no Weyl particles or no massless fermions in nature, why do we care? I mean, why are we talking about these anomalies and these things? So I think that at the beginning of these chiral things, we care partly for the fun of it, and partly because of a very good reason, and it was the decay of the pi 0 into 2 gammas. That was a process that was forbidden if you had a left-right symmetry, an axial symmetry conserved, and that was immediately seen that it gives rise to the to the good time or whatever, if you think that this anomaly, that this thing is not conserved. So there were these two reasons. First, that nobody could stop physicists on this time to explore something if it was fun, and even if it didn't exist. So the question is not only for fun. There are places where we can study the properties of these chiral particles, even if they don't exist as free particles. So you will not study this physics that I'm going to describe now, say at CERN, where all the particles are really recollected into left and right partners. But there are places to study. So while fermions, remember a single chirality. So you have to be Dirac and massless, because if you're Dirac, everybody comes in chiralities also. So as I said yesterday or the day before, the spinor representation is a direct sum of the two chirals, say. So any spinor 4 dimensions, U plus, U minus, can be collected like that. And this is an eigenvalue of chirality, and this is also, but mass mixes the two chiralities. And then you never have like a single Weyl particle, okay? So definition, what we are talking about and what the anomalies will act upon are Weyl fermions, single chirality in a Dirac fermion. So for any hope to find that, so separate the chiralities and being able to study each of them differently will be always associated to massless Dirac particles. And on top of it, you have to separate the chiralities. That's something that can be done in 2 labs, say. In the so-called quark-gluon plasma. That's the plasma that forms when when 2 heavy ions collide. They are heavy ion collision experiments, and when this match, these heavy particles for fractions of a second that are ridiculous for a very small time, it forms a plasma with such a high temperature and density that the masses of the constituent, the quarks and maybe even the electron, can be neglected. So energy is, the typical energy is much bigger than the masses of the particles, of these bosons. And they also form enormous magnetic fields in such a way that the left and right chiral constituents. So first you deconfine the quarks that are inside the proton or the whatever you smash. And then the enormous high magnetic field are able occasionally to create densities of left and right particles, okay? So nobody is massless, but if the energy of your events is big enough, you can hope to find some prints of this chiral anomaly. The prints is what I'm going to discuss now. So what is the anomaly and what are the consequences? But in high energy, you can have these 2 labs, early universe. So as you can imagine, it's not easy to make experiments in the early universe. You can observe things, but make experiments is difficult. In the quark-gluon plasma, they are making experiments. In particular, there is a strong search for the chiral magnetic effect that I will describe later. It looked like they were about having it, but I think it's still uncertain. But anyway, very difficult labs. And now it comes here, something unexpected, in condensed matter. In condensed matter, recently there appear crystals. Not only, some of them were there, some of them are being made artificially, which have the Fermi surface, where they have two bands crossing at, in the brilliant zone. And it so happened that sometimes the Fermi surface is right at the crossing or nearby enough so that you can discuss the system, the low energy system, as in the spirit of Landau, as a chiral particle. In particular, there are chains in 1+1 that are chiral, but this is there are chains in this their own right, and also very important. I will discuss it later. If you have a Dirac system and you apply a strong magnetic field, then everything is projected into the lowest Landau level. That happened to be a 1+1 chiral model. So 1+1 is not necessarily associated to chains, but it is also any system that is described with the Dirac equation in the extreme, I don't know how it's called, this limit, in the extremely quantum limit, no? In a strong magnetic field, yes. You get is a time and a space dimension, right? Yes. So what happens is that if you say put in a fermion system, you apply a very strong magnetic field, say in the C direction, then it so happened that the Dirac, the Landau modes organized into Landau levels that are, square root of n or whatever. They are very different than the standard Landau level. So in the standard Cp square over 2m, the Landau levels will be equally spaced, and there is no zero energy mode associated to any n. While in the Hamiltonian given by the Landau physics, or in Dirac systems that I will later show you how they arise, a strong magnetic field projects, the Landau levels are very different, and then you have, if this is P set and this is the energy, you have a chiral zero mode, say that this is a left particle, then you will have dispersion equals to Vf times P set. In fact, it's plus minus P set for the plus and minus chirality. That's the way it is. So if you have a Dirac system with two Weyl fermions, what you will have is exactly the two chiralities. And then those high Landau levels will be degenerate and will contribute nothing to the anomaly that I'm going to describe now. So all the physics is projected into this 1+1. Of course, if you're in 1+1 strictly, all the things that I'm going to describe occur in a simplified way, but okay. And if you are in 3+1, then what happens is that the density of states of these zero Landau levels is proportional to B. to the strength of the magnetic field, but everything else is like 1 plus 1. Okay? One space, one time. It's the seat. This is 1 plus 1, right? Energy and P. And that's it. Or maybe I'm missing your question.
I don't know what my understanding was, that maybe projecting the S wave, S wave only, where one dimension moves. Then you can project chiral 1 plus 1 because from the radial direction of time. But maybe I'm wrong.
So I think the point is that, so how many dimensions you might work?
3 plus 1.
3 plus 1.
It's 3 plus 1. So, I mean, then you would expect some surface, object, and then...
No, I don't have any boundaries. Why? Because I'm always talking about effective theories around the Fermi surface. I don't care what happened beyond. I'm not going to discuss any topology or anything. I'm just infinite quantum field theory, effective action of what happens around the Landau, the Fermi surface. That's what I'm going to discuss about. Okay? Anyway, so in condensed matter, if you happen to have a solid, a crystal, that is describable by the Dirac equation, and I will tell you that there are a lot of them now, then, and you apply a high magnetic field, then all the physics, all the low energy physics, or all the anomaly physics will be driven by these 1 plus 1 chiral modes, the 0 modes of the Landau levels, okay? That's the first. Then in 2 plus 1, of course, there is graphene. If you probably have seen this sometimes, but anyway, graphene has a dispersion relation that is very complicated in the Honeycomb lattice. But what is important is that the Fermi, it has Fermi points instead of a Fermi surface, meaning that the dispersion relation happened to be like split into upper and down plane, and the Fermi surface cuts exactly in the middle. So this is all coming from the Honeycomb lattice that you all know. And you know that it's not a bipartite, it is a bipartite lattice, but it's a lattice with a basis, right? So it is two-dimensional, but you cannot go, say, you cannot go from one point to any other in the lattice, just moving from here, I move with the lattice vector here and here, I will reach any point, right? There is no lattice vector here, even though being two-dimensional, such that you will reach any point of the lattice moving with one lattice vector. You need at least two. For instance, say that I declare that this is a lattice vector. Also, from here, I can come here, and well, this is a stupid lattice vector, never mind. This one, I would come here, and I would rotating, well, you know that they are black and white points, right? That they are not equivalent. And this obliged you, when you do this tight binding and try to get the dispersion relation of graphene, to use a wave function with say, two sides, black and white. So it's hard to say that graphene is a Dirac material, right? It is, because when you write down the dispersion relation, because of the Honeycomb lattice, just because of the geometry of the lattice, then you end up having, but this probably you know, and I don't want to stop too much into it, but graphene 2 plus 1 it has a Hamiltonian sigma dot k. So it has exactly a Weyl Hamiltonian, but the point is that this sigma has nothing to do with the spin, or it has to do with this lattice degree of freedom. It's something that you have 2 points in the unit cell, and then you get a Dirac equation. Something very important of this graphene is being 2 plus 1 implies no chirality. Because, as I told you last time, the chirality operator is built up of a gamma 5 matrix that only exists in even dimensions. So graphene doesn't have any chiral anomaly or anything. What it has is a parity anomaly, which is an anomaly associated to a discrete symmetry. It's a lot of fun, but it's not chiral, okay? But it's a Dirac system, say, spinless, but Dirac, okay? So now I will call a Dirac spinor to somebody that obeys the Dirac equation. And I will not care where did this equation come from, okay? So I'm trying to tell you more or less what is the origin of the confusion between Dirac in high and in low energies. So in the last lecture, I would call Dirac to a representation, a firm spinor representation of the Lorentz group. Now that I am going into condensed matter, I will call Dirac to a solution of the Dirac equation. And I don't care about the origin of these sigma matrices, all right? Fair enough. So wrapping up, the reason why graphene is not chiral is not that the degrees of freedom of sigma are in the lattice or in the 2 points in the region zone. It's just because it is a 2 plus 1 system, and there is no chirality there. I don't know if I asked you to do this exercise of proof that in 2 plus 1, the gamma 5 matrix is like the identity. If not, you do it. If not, I'll keep this blackboard for the exercises. There will be a lot today. So, I mean, see if you can construct a gamma 5, same as usual, gamma 0, gamma 1, gamma 2. Why not? You don't have the 3, all right. See if it can be, each square have to be 1, it commutes with everybody else, and see if it allows you to classify in 2 plus 1. You will see it does not. Of course, the confusion about chirality in graphene is because, as I told you, the parity operators switch the chiralities. And then there is certainly parity in any dimensions, but not chirality. So you have two things that are related to parity, but those are not chiral people, and they will not have the chiral anomaly. Now, another system, which is other systems, this is my favorite, those Weyl semi-metals. Those I'll show you later in the screen, how they look like and what are they, but they are band crossings in 3 plus 1, where the Fermi surface lies around those points. So those are really vile people. So, but I will discuss more about that later. Okay? So wrapping up, the chiral anomaly has always been there and is a lot of fun in high energies, but it is very hard to do experiments and to observe. And what condensed the fresh air that condensed matter brought us were like tabletop, they call experiments, where you could perhaps test the consequences of this anomaly that I'm going now to introduce. Suppose you start with the massless spinor, 3 plus 1. What I say is also applicable to 1 plus 1, and some many other ones, but plus ones, but we will stay in more physical dimensions, which are these two. Now, the spinor, as I told you, if it is massless, the Dirac equation splits into two, 2 by 2 equations that are the Weyl equations. Essentially, what is important, and here is where it comes the massless situation, is that left and right fermions are independent, so you can do an independent left or right rotation of the face of each one, and you will have a symmetry. So you can do something that I will call a vector rotation, means that you rotate left and right the same angle. And then this gives rise, via the Nether theorem, to a vector current. Which is something that I already asked you to do an exercise about. So I remind you, Nether theorem says that continuum symmetries of an action give rise to conserved currents and conserved charges. So if in such a massless Dirac fermion that is split into two Weyl fermions, left and right, remember those are two-dimensionals, this is a four-dimensional thing, you can do this, and then you get a conserved vector current and a conserved vector charge, which is the integral of J0, right? This charge is associated to the conservation of the sum of left and right fermions. But you could also do a rotation, an independent rotation, so rotate differently the left and the right fermions. And you would get also a conserved current, which, so we will define the axial current. This is a fancy way to say that left are rotated by alpha and right will be rotated by minus alpha, okay? And then you get J phi current. Which is conserved. And has a conserved charge, Q5, which is, say, the number of L minus right particle, it will be conserved, okay? So far, so good. Now, you add a background gauge field, or you add a background electromagnetic field. When I say background, I only mean that I will not pay attention to the dynamic of the gauge field. The gauge field will be just there, and this is what you have in experiments, okay? So if you add a background gauge field, then you get an action or a Lagrangian or whatever that is gamma mu, d mu, without f mu nu, okay? And maybe with an I here. So if you do that and you compute the divergence of the axial current, you see that this is not zero. It's something divided over 4 pi squared. You get what is called the chiral anomaly. This is the simplest version of it. You can make it more precise and more complicated, but so far, I'll keep it like that. Let me see if this 2 pi is 2 pi or something else. Could be. It's 16 pi. I don't care. But since you're taking notes, you write 16. Okay? Are you shocked about that? No? You should. Why? Because, you know, we are insisting always in symmetries. Symmetries are very important. Symmetries is what the things we build our effective actions with. And this axial symmetry is an important symmetry. And it is amazing. You add the background field and quantize, of course. If you stay at the classical level, this will not happen. You quantize the field, you add, so exercises here. So far, I just wrote down through this on U and call it chiral anomaly. I will explore it, of course. First of all, I should define what this dual tensor is, because otherwise, how would you be shocked or anything else if I'm throwing their things and don't say what they are? So first, this dual electromagnetic field is defined as, I don't know if it has halves or not, but I don't know. Proportional to epsilon mu nu rho sigma f rho sigma. That's the definition of the dual of the electromagnetic tensor, okay? That's the definition. You will see later why, how it arises, but by now, you just take it as it is, and I want you to make a couple of exercises, which is first, see that f mu nu square, which is what appears in the action of a free electromagnetic field, is proportional to E squared minus b squared, while f dual f is proportional, is E dot B. This is an exercise, funny. I mean, it's fun, direct, stupid exercise, but I just wanted you to know a little bit what this is F dual, what is it and what is it doing here, okay? Another thing that I just, another exercise about this F twiddle, or you will see it also as F star, or anyway. So why it is called dual? What is this duality? It's a dual because work out the fact that the relation of this F dual with the EB, with the electric and magnetic field, is the dual, or the B and E are exchanged. So the magnetic field in terms of the dual tensor will be F0I, and the electric field will be related as this one, HIK, EK. Okay, those are exercises. Just to give you a feeling of what F dual is and why we call it dual. So now of course, if not me, you should be asking a lot of questions. So first is, what is the origin of the anomaly? And second is like, what do I care? I mean, why would anomalies, this kind of anomalies, apart of being annoying, awake new physics? Why would they be producing new transport phenomena in particular? Okay. Those are two fair questions that I will try to answer. So we didn't have these anomalies in the classical field theory. And I told you that quantum field theory is just quantizing the classical field. So what did we do wrong when quantizing or what is going on here when quantizing the quantum field, the classical field, so that we are getting anomalies? And the reason, basically, is that we have infinite degrees of freedom. What gives rise to infinites in many disguises. So you are computing correlation functions, you find infinites. You are computing the current, you find that is ill-defined, you have to regulate it. So you need regulators. I'll give you an example afterwards. And second, the reason that why anomalies are induced in new transport phenomena is because they add new terms to the effective action. And remember that we got the responses like adding J mu, A mu, or adding sources and to the operators and then deriving with respect to the operators. If you change the effective action adding new terms, then you produce new transport phenomena, and I'll give you some examples of this later. Okay. Okay, exercise. Derive the chiral anomaly in 1+1. This is a lot of fun, very easy, say, because in 1+1, everything is nice and workable. But quite everything that I will leave to you as an exercise is in the tongue lectures that I wrote in the program. But these ones are not in the quantum field theory, but on lectures on gauge theories. They are in the wave gauge theories. So everything is worked out there very nicely and simple, and without misleading things. So it's simple, but not, okay? Anyway, before going further, I just, when I see the anomaly like written like that there, and I see the definition of the current, I will ask myself, what the hell? So the current by the way, see that in this electric current, well, that's not the electric current, that's the axial current. But see, if you are if you were educated in condensed matter, you're used to the fact that currents are proportional to velocities or momenta, right? Because p squared over 2m, then the current is like the derivative of the expression relation with respect to p is p. Notice that in Dirac, if you are in high energies, this is your daily life. Of course, you wouldn't even ask why there is not a P in the current. But in Dirac, there is no P in the current. There is no derivative in the current. Because, of course, the Lagrangian is linear in derivatives, okay? So this is the axial current. So the first thing I would ask myself is, how comes there was nobody here there is no derivative even here in the current. So how did this A mu pop up in the form of F dual F? This is really amazing. So there will be, you will do that later as an exercise, but I'll give you a hint of how this electromagnetic field pops up, which I think is very interesting. So, anomaly from point splitting. I think Jerome told me that he was deriving something from point splitting. So here you have another exercise to do, which is, what is interesting to me, what I want to point out here are two things. First, this every composite operator, and composite operator here is not in statistical mechanics way. A composite operator is an operator made out of fields and derivatives, and that's it. And this is what, when computing the expectation value, will give rise to observables in quantum field theory. So In particular, this current is a composite operator. It's a local operator because we insisted, because we wanted to have a causality that this is something that depends on x only, not on x and y. So x Cx B, you know that the commutation relations of these fermions is like delta AB, and then a delta function of x minus y, okay? Mu and whatever. So you cannot have the two fields here defined as the same point, because this is a singular, very singular thing, okay? So here is the easiest, the first place to think where is the origin of these anomalies. Okay, so what is point splitting? A way to define this current is define J5 mu as the limit when epsilon goes to 0, psi at x plus epsilon half, gamma mu, gamma 5, m psi at x minus epsilon half. Okay, this is what is called point splitting. Yeah, 3 more minutes and I'll be done. Now, my only aim here is just to show you how does the electromagnetic tensor pops up in the anomaly. If I say it's a background field, it does nothing. So how comes that it appears right here? And of course, anybody has any objection to that definition? No objections? Now, think of gauge invariants. Objections? Sorry? Bar? Okay, bar. Now, this is a mild objection, you must admit. Now, I mean really objection. Okay, so exercise. Show that bar is not gauge invariant. Or, well, I'll make it easier. And when I say gauge invariant, I don't mean that I'm adding any external field or anything. It's just that I do an e to the I alpha rotation in X and an e to the alpha rotation in Y, and this product is not gauge invariant. This you know, and this is an objection you have seen, and you should have be very smart and say, oh, you need a Wilson line in order to make this gauge invariant. Okay, so please do this exercise because this is really a very interesting exercise if you've never seen it. But in order to make this thing gauge invariant, you need what is called a Wilson, in that case, line, which is, you need to interpolate here or wherever in the middle of this current. Invariant, the integral of epsilon x minus epsilon half to x plus epsilon half to e to the integral, a mu d mu. Let me see if this is correct. Okay. Yeah, just a minute. I may have made all wrong. Okay. This is what you need to add here to restore the gauge invariance of this current. Okay? Yeah.
We're talking about local gauge invariance, right?
No. It's global. Only you see. No. It's a global gauge invariance. You get this from global.
So alpha is not
I mean, okay. So, what you do when you do this psi going to e to the I alpha? Yeah, you're right.
alpha is
Yes, yeah, alpha dependent. Yeah, otherwise doesn't make any sense. All right. So, you never seen that? Maybe, okay, maybe then I will be more precise later. Yes.
I mean, we should get current with gauge invariant, like current, if we just follow the Nether procedure, right?
If you follow the Nether procedure, you get a current at the classical level.
Yeah.
Now, when you try to quantize the field, you cannot define psi x and psi dagger x at the same x. And there is where the gauge invariance is in challenge. Okay? Here, you don't like it? Then was the question? You see the gauge transformation is d mu, is a mu goes to a mu plus, I don't know, 1 over e, no? D mu alpha, or something like that, no? Okay, you choose your own convention. We would never discuss about conventions. I buy yours. Yes. E is 1, I agree. You want e square up there?
No, but I mean, we take e as 1 there.
Yeah, okay. So you can find this like with an e square here and take it to 1. The reason why I wrote a 1 is because I'm going to tell you later that this anomaly is fixed by the chiral content of the standard of the model that you have. And so it's a sum of how many left, how many right, in which representation on TA, TB, and then you get a number. So, of course, when you go to the lab and you switch on an electric field, then you will get an E square. So in the transport, you get an E square, but I didn't want to put it there just because I'm going to emphasize later that this anomaly is something that doesn't depend on the existence of the gauge field. And this is important, but okay. But again, we won't discuss about the notations. Well, I'll stop here and wrap up later. Okay. Yes. So what I say is that I'm giving you an example that of a symmetry that you had in the classical action via the Nether theorem, and it cannot stay, or it doesn't stay in the quantum action. There are a lot of details here, but I think that you should really work them out in the books or whatever, and get the important, say, message, which is the following. So let me first continue with this Wilson line. Well, this is what it is. It's nothing to do. But it is very interesting to see the relation between this Wilson line and the von-Aronoff effect. So I'll write a 6 here. Well, first you convince yourself that you need this Wilson line in order to get something that is gauge invariant, local. Somebody pointed out it's local, of course, because then it's alpha x minus alpha y what makes the things not invariant. So study the Wilson line. I thought you did it already, but okay. The Wilson line, and mostly the Wilson loop, which is what is related to the von-Aronoff effect. Now, this necessity of a Wilson line in order to make this gauge invariant already introduces at least something related to A mu, okay? So that gives you a hint that it's not so strange that you will get the F mu nu in the anomaly. Work out this, because I want to go really to matter. Work out the point splitting anomaly, details splitting, here in Tongo, or wherever you want. But there are a few steps. It is a very interesting calculation because it tells you where the anomaly really resides. And you will see, for instance, that once you define this current, you choose this regulator of a Wilson line here. Then you see that when you take the derivative of this G mu, using the equations of motion, all the derivative of the size drop, and the only thing that you are remain with is the derivative of the Wilson loop. So this is that's one of the things that is interesting, and also you have to use. So I'll tell you what are the tricky points, that just to give you an idea of why this F dual F appears. So that first there is this Wilson line, I call. Then there is Tricky point in the calculation is first Wilson, then there is a property of the fermion propagator that says that when epsilon goes to 0, this limit of psi dagger So there is a fact about this fermion propagator that you know that is gamma mu p mu over p square, mu over p square if you're free, and then if you do it properly, you will see that the most singular part of the propagator when these 2 points are going together goes like this. And it tells you that this is an ultraviolet divergence. So the origin of this anomaly is ultraviolet in the sense that it is because of putting things in space together at the same point, which is equivalent to putting things at infinite in p space, okay, in energy. So, and well, this is something tricky. And then the third tricky point that you may find in this calculation is just nothing. Then you have to use the properties of the gamma matrices, no? Which are quite straightforward. So you do it. Do it in 1 + 1. That's very easy. And then if you're brave enough, go to 3 + 1. It's just, it's perfect. It's a calculation that you can follow in full detail, but it's long and I don't want to go into it. Sorry? Sorry, I don't get your question. Say it again. We will not do that. Okay. Yes, yeah. Huh. No, no. This anomaly is totally independent on the gauge fixing. The gauge fixing comes later when you want really to do a QED properly, and do loops and things just to eliminate some of the degrees of freedom of the gauge field. But here it doesn't play a role. Yeah. In the anomaly is a fixed background. No, it's not.
So you don't have this problem.
Yeah, the F mu nu squared does not enter into the anomaly at all. Okay, so you do that. What I want to emphasize is that, notice the following. I haven't yet defined quantum anomalies, right? So I'm starting giving you an example of something that was classically conserved and is not conserved at the quantum level. But now I will go and define. So exercise 8. Show that the chiral anomaly in the 1 + 1. Well, study or read is a pleasure, mostly for lattice people. study the original Nielsen-Ninomiya paper. Not the one that says absence of neutrinos in the lattice, which is a topological thing that is also a pleasure, but not such a pleasure. The simple one, the one that says that the Adler-Bell-Jaquib anomaly in the lattice. That is very interesting to see also why do we get anomalies in a high energy and we don't get them in condensed matter, even though we have the same kind of systems. So this is a physics letters B. Now I'm messing up all my notes, never mind. But you look for it. It's the Adler-Bell-Jaquib anomaly in the lattice. Sorry, just a minute. Okay. So the exercise that is very nice is if you, I'm looking for the reference of this Nielsen-Ninomiya, but I didn't find it. That's all right. So in this reference in the original, so you work out the anomaly in 1+1 and get this nice equation. E dot B. This is nice because this is what experimentalists use mostly in order to deal with the anomaly. So if you go into 1+1, see how F star F or F dual F is. It's just an electric field because there are no magnetic fields in 1+1. And then you see that the whole anomaly reduces to this equation. You may ask then, what is B? And B is, but this is not 1+1, sorry. This is the experimental list. And they get it from the 1+1, where you get this E, by adding the degeneracy of the Landau levels, then you get E dot B in 4 dimensions, reconstructing. But in 1+1, I don't know how it is. Never mind. Okay. So once we get this axial current anomalous, we could ask, can I remove the anomaly somehow? And why I'm saying that is because currents are defined up to derivatives. So maybe I will find a way to add something to the axial current and let it be conserved again, right? So in particular, there is an exercise that you have to prove which is proof that this F dual F can be written as the derivative of something. And this something is mu nu rho sigma, this Chern-Simons current. I want what? I don't want anything. So mu nu rho sigma. Okay? So this is an exercise proof that is just massaging the definition of a mu and so on. So a fair question is, since the currents are defined up to derivatives of an antisymmetric tensor, so that when I, so currents tensor, any, or I call it that is not taken. Well, okay. Why this? You can always shift the current by the derivative of an antisymmetric tensor, because when the only thing important of the current is that the mu j mu will be 0. And this term will disappear from when you take derivative. So you can always shift this. So now, you could imagine, you can think that the axial current can be made again conserved just by shifting by this Chern-Simons term. But it so happens that when you do this, you spoil the vector current, right? So you can show that. So can keep J mu 5 if you like it, conserved, but then you spoiled G vector mu. This is obvious in 1 + 1, where the vector current, the axial current and the vector current are related. So prove this. Prove in 1 + 1 that you can shift the anomaly from J axial to J vector. Another thing I wanted to tell you is that this anomaly can be found in many different ways. The typical classical place where you find the anomaly is the original one, is the Adler-Beljac way, which is associated to so a fact important. When you say that the current J mu is conserved quantum, the quantum conserved at the quantum level, it means that this current can be inserted into any correlator, and you will always get 0, okay? So another way to see the anomalies is that the mu. Okay, So the classical way where you see the anomaly is always associated to this graph that Adler, Bell, and Yakif wrote, is associated to the pi 0 going to gammas. Okay? So if you want to compute the transition, the probability transition of a pi 0 going to 2 gammas, then you encounter at the one loop level this kind of triangle diagram. And then you see that this triangle diagram is infinite, but then, you see it can be split into two, and then the two are infinite. When you subtract, you get a finite thing, but it's not determined. So you can subtract differently and get a different result. So the case of the anomaly is a very nice case, which is not that the result is infinite, it's that the result is undetermined. It's not, there is a very nice paper saying when something like when infinities are not infinities, but undetermined. In any case, this is the classical place where you will find the anomaly. And there, the reason why the anomaly is only in J5 and not anywhere else is because from the beginning, you pick up a regulator in computing this graph that keeps the vector symmetry conserved. And then you break the axial. You can also imagine that you do Pauli-Villars regulation of this diagram. If you do Pauli-Villars, means that you introduce a mass. Again, you break the axial symmetry by introducing a mass and preserve the vector symmetry. But symmetries can be shifted from an operator to another. So, definition. Definition. We have a quantum symmetry, anomaly, sorry, when you cannot find a regulator that keeps all the symmetries of the classical action symmetries, okay? So a quantum field theory is anomalous when in the way of regulating your things, you cannot find a way to regulate the things that will keep all the symmetries of the classical action. Symmetries of the classical action. So, wrapping up, why do we get anomalies in quantum field theory? Because we have infinite degrees of freedom, because the spectrum is infinite. There is a very nice way to derive the anomaly also, like with the spectral flow, and I think that this was done by Professor Capelli in his review very nicely. And there you see very easily that the only way you can flow from left to right without, consistently is if there are infinite people down there at minus infinity. We say that if you want, that's something that in the lattice is obvious that this thing exists of going from left to right, but there you always have 2 points. I'll go to that later. You always have 2 Weyl points in the lattice, so there is a spectral flow, say, that you have 1 plus 1, because you are in a magnetic field or whatever, and everything is filled here. This is left, this is right. Then this is the 1 plus 1 anomaly, no? So This was PC, I said before, that's the energy. You switch an electric field, EC, and then you see that these electrons that have dispersion relation plus minus PC, those will move up and those will move down. So what an electric field does, in fact, is transfer left to right. Okay, this is the spectral flow vision of the anomaly. And this is something that happens when E is parallel to B, because first you put a BC in order to get to the zero lambda level, then you apply a EC, and then you get something that is what I wrote before, which is the N5 dot is proportional to E dot B. Okay? So the point is that if you are in a lattice or in a condensed matter system, what would happen is that you will not have only a point like this, but you will have another like that. Why? Because the Brillouin zone is periodic, compact. You cannot have a dispersion relation just going up to infinity, right? So this is what happened in lattice and in nature. And there is a theorem that forbids having Weyl points, having a single Weyl point, okay? So maybe we are back to the question then, what are we talking about? Because if in nature you will never find a single Weyl point, why are we discussing that, and how is it possible that we will get any print of the chiral anomaly, right? So I'll come to nature now. Now, but before, I just wanted to say another important thing. So first, currents can be shifted, so you can play with the chiral and vector, but of course we prefer to conserve the electric charge. So for us, the vector current will be holy, and the axial we can give up. Okay, so, but this is a choice. Later, when we see the gravitational contribution to the anomaly, we will see that you can also, when we see gravitational anomaly, or maybe the conformal anomaly, you can choose between breaking the conformal anomaly or the conservation of T mu nu, of the energy momentum tensor. So you would choose the conservation of the energy momentum tensor. So just be aware that it's not that the axial charge is not conserved. It's that some of the two charges has to be broken. And there is no way to avoid that. So the anomaly will be there. And another thing important also, too important, is that anomalies are a property of these chiral fermions. And they will be there even if you don't switch on any electromagnetic field or anything. What I mean is that you will always find that this correlator is anomalous, is non-zero. So say that we decide that to keep the vector charge, then you will find that this is non-zero, even if there is no electromagnetic field around. Okay, then what? Then going back to the question of how the standard model is organized, standard model is organized in multiplets of left and right people. At the end they combine, but left and right, and they are these chiral anomalies, they are built in the model. So if you look at the divergence of this J mu, you will find a coefficient that depends on the content of the chiral people, and which is a number, and some operator, which is like E dual B or whatever, irrespective of the fact that you apply or not a background field. What happens is that when you want to test the anomaly, to ignite the anomaly, then you use background fields. But background fields are not necessary to describe anomalies. Anomalies are there, okay? Any questions about that, because this is important? Yes.
So my understanding is that you can have a spectral flow in classical systems.
Yes.
So, like, how I'm struggling to connect that to the definition of a quantum anomaly.
Yeah, you can describe this anomaly as a spectral flow from minus infinity. So it's like, yeah. So imagine that you don't have this other point to absorb what you produced here. So if you only have a chiral system, a Weil fermion, then there will be infinite, say, in the Dirac that we decide that there's no need, but okay, there will be infinite states to be pulled to the right-hand side. So there will be spectral flow, or like that. But the reason why this is anomalous is because there are infinite people there. There are many analogies with some hotel and some things that I don't really understand, but say that in finite system or in lattices or in nature, you will have just electrons coming from here to there. Not everything is conserved. Here in quantum field theory with a single Weil fermion, you will have infinite spectral flow. Okay. Okay, so let me show you now. I was promised that this would work, but. Okay, it works, good. No, you just, okay. No. Okay, this is more or less what I told you. Well, maybe I will not touch it. That's what I told you about. No, it's my computer that never mind. So this is what I told you. Now, what I wanted to ask is the following. View. Okay, that's what I told you about the behavior in a magnetic field. When you have a standard system with p squared over 2m, you will get these Landau levels with no zero mode. And when you are Dirac, then you will get those Landau levels there. This omega is the cyclotron frequency. And then you see that there is a zero mode at n equals 0, okay? This is just for a left particle. So if you had Dirac, and the two left and right would be superimposed at the same point, then you would get exactly this kind of stuff, no? Doubly degenerate people up there, and two chiral 1+1 fermions here. And this is realized in nature. So if you take graphene, although it's not chiral, it doesn't matter. You apply a magnetic field, you will see with your eyes these Landau levels. And in fact, that's funny, in the original paper of graphene, before the Nobel Prize, the title of the paper was not how nice is graphene or whatever. It was like Dirac fermions in a condensed material, in a honeycomb lattice or something like that. So they emphasized the reason that they emphasized that they were Dirac because they found this spectrum there. So it's very interesting that the Landau levels of graphene were the smoking out, whatever, of the fact that graphene obeyed the Dirac equation, okay? That's interesting. Now, Dirac matter. As I said, this is either people that have left and right points I was offered a pointer and I neglected it, never mind. I use that, love it. So this is the Brillouin zone of graphene, of the honeycomb lattice in 2 dimensions. It looks complicated, but what is interesting is that the Fermi surface at half filling lies exactly here, and then there are 6 inequivalent, 6 points that they are caught by the Fermi surface. Only 2 of them are independent because of lattice vectors. You can go from, you can relate. So these left and right, they call it left and right. That's the first confusion, you know. They are not left and right, they are 1 and 2, okay? So these 2 points called left and right are at the origin, at the heart of the Dirac behavior in graphene. And as I told you, it's very interesting, both papers, there was first Geim and then Philip Kim, came with the same emphasis that look at my Landau levels. I am a Dirac system, okay? But there is something I also wanted to call your attention upon, which is the following. Okay, this is a cone, good. But this is a Brillouin zone of somebody, like this one. Those are Dirac semi-metals. The point is that the slope of this cone is not c, is not the velocity of light. So this is not a light cone. This is a cone, I agree. And this is a dispersion relation of a massless particle. But this massless particle is not a photon. And not even a neutrino should supposedly to be massless. Massless people do have to travel at the speed of light, this period, right? If you take the Einstein relation, the dispersion relation, if you're massless, there is no other way. You have to move all the time. You cannot be at rest. And you have to move at the speed of light. So it is fun to see that at the level of a free system, if you don't add an electromagnetic field, those Dirac matter people will be perfectly relativistic, okay? So a conical dispersion relation, only the light cone is a bit different. Now, what happens when you insist on having experiments with electromagnetic fields? Then you are in trouble because light will insist in propagating at the speed of light. And then what you get is a breakdown of Lorentz invariance. What am I breaking? I'm breaking boosts, of course, because for a boost, you need a precise velocity. Remember that there were, I don't, x prime, x minus v, t, no? T over something, no? Well, like that. But this gamma was 1 over square root of 1 minus v squared. That's the velocity at which your inertial frame moves. And this is the speed of light. Now, if you want to make a boost when you have light and also somebody that has a different slope, you're in trouble. So these condensed matter system are Lorentz breaking, but They're Lorentz breaking, but we don't care. So now I lost my own. Jesus.
Your laptop, the problem is with your laptop or with
I don't know.
try, okay. But to the point there is
Okay,
okay.
came back.
You can press F3 next time.
Okay, thank you. Okay, so notice that these condensed matter systems are not fully Lorentz invariant, but it doesn't matter. So this is a warning. Plus, this is something I love, This is about how is QED in graphene. I don't have the time to go into it, but it's a very nice subject. Basically, I will tell you what is interesting here. When you try to build up your QED, now I have a fermion, now I put an electromagnetic field. In graphene, you see that the fermions are confined to the plane, but photons, of course, are three-dimensional. And then the propagator of the photon in this fermion, this graphene system is weird, is very special. And this is what is called brain-reduced QED. But it's funny, you predict a lot of things. We did some work in the prehistory of graphene and of physics, in the 80s, predicting that the Fermi velocity would renormalize in the presence of an electromagnetic field. And this was a paper that remained dormant for 20 years. And then when graphene was discovered, they measured the renormalization of the Fermi velocity. Then the paper became, this is what the editors call a sleeping beauty. It was sleeping for many years, and then it became very popular. It doesn't matter. What is fascinating is the fact that we were, for the fun of it, exploring the electrodynamics of graphene, and got the prediction. There is the Fermi velocity will depend on the energy. Something's very weird in condensed matter. And then they found out the way to reinterpret it and to measure it, and they did. So the most interesting people are these Weil semimetals, because they are 3+1 materials. I say Lorentz breaking QED, but the breaking is very mild because it's just that the cones are not light cones. And then you can build up an action which is exactly QED, apart from the fact that the gamma matrices will be multiplied by VF. If you do that, then you can apply all the things you know in QED into these materials. On top of it, you will get anomalies in everything. Now, why do we aim to measure anomalies in these systems? First, this is showing you more or less how the brilliant sun of these people look like and how are the bands. So the idea is you look here for a band that at zero will, for some crossing at zero energy, and then you find here, for instance, these crossings here. 2, 3, well, 2, 3, no, 2, 4, 8, whatever. Here is again is a mess, right? So if you are a Weil semimetal, you have to find a band crossing near the Fermi surface. You will not find it because your eyes are not trained for finding it, neither are mine, but the material people are able to select Weil semimetals among these horrible people. Well, they are not horrible anymore, but they used to be horrible to us. Like in the periodic table, they were people that you never knew they existed, and now they built very nice Weil semimetals. What happened in these people is that there is not just a nice Weyl cone. There are many pairs of Weyl nodes. The cones are not nicely tied like that, like a plus minus p set is like messy, so they are anisotropic and they are not real cones, but it doesn't matter. They are Fermi arcs, that I don't mind. The Fermi surface doesn't like exactly at the Dirac point, and there are other trivial bands crossing the Fermi energy. So the question is, any hope to observe chiral physics here? And the amazing thing, which is what I wanted to tell you today, is that the chiral anomaly, this is the way they like it. It's like in 1 + 1, but okay. Has been observed in experiments. Now I think that there is no question about that. And in many papers. Even the chiral magnetic effect that I didn't talk about it yet is one of the anomalous transport coming from the anomaly has also been observed. And even the gravitational part of the chiral anomaly, well, okay, anomaly-related transport is once you have this chiral anomaly, then you can work out that you may have this transport phenomena that are new. This comes from the quark-gluon plasma. This is this energy diagram where you find people, no? So the chiral magnetic effect is electric current proportional to an applied magnetic field in the presence of a mu5 chemical potential means an imbalance between left and right. So say that you would need here to have like a chemical potential that would be here like that and here like that. Of course, in equilibrium, there is no chiral magnetic effect, but there are ways in condensed matter to persuade, out of equilibrium always, to persuade these people to be, for a while, in a chiral situation. And there is where you see the chiral magnetic effect. And what is amazing, really amazing, is they measure things that are prints of this chiral magnetic effect. Then there is an axial magnetic effect, which is the generation of an energy current proportional to a B5 field. I mean, an axial gauge field. Axial gauge fields are not in the table of particles at all. They would be harmless. They would do very bad things. We don't want axial gauge fields. We don't have them. But again, and this is in the presence of any chemical potential, and also the axial chemical potential would drive it. But if you have a normal system with some little filling so that you would not spoil all the Dirac physics, because these Dirac semi-metals, it happened that when you dope too much, when you put electrons on it and you fill up like too much, then they become Fermi liquids. They lose the remembrance that there was a Dirac point there. But anyway, axial gauge fields do not exist in nature or in particle physics, but they do exist in condensed matter, and they are wonderful people because you can get axial gauge fields from stretching, from deforming the lattices. And this is a very beautiful thing that happens. And again, you can ignite the axial magnetic effect in condensed matter. Finally, there is a chiral vortical effect, which is the generation of an electric current when you rotate the system. This is very similar to this, with the vorticity playing the role of a magnetic field. You know that rotating and magnetic fields are very similar in many ways, no? But that needs both gamma 5 and mu. And what is interesting here is that those coefficients that are associated to the anomaly have a very well defined dependency with the temperature. And then this one of the reasons why in experiments they say, oh, I have seen the gravitational anomaly or the whatever anomaly is because the behavior of their measurements with the temperature go. Now I'll tell you what do they measure, and then we are done. Well, since I didn't speak about gravitational anomaly, I'll leave it for the next session. No, that's it. Okay, so what do they measure to say that they are seeing the chiral anomaly? What they measure is they measure conductivity that is, sorry, I'm done, proportional. So they put an electric and a magnetic field perpendicular, this is the material, B, E, and they are able to change the angle between B and E, external magnetic field, or external, of course, and an electric field. And what they see is an enhancement of the conductivity, electrical conductivity, when E is parallel to B. So basically, this is what they see. Magnetic fields are in all the labs. Measuring resistivity or conductivity is everyday experiment. What is now easy is to get the Weil semi-metals, but there are now people constructing them. And with this, I am done. Thank you. Yes, I'm very sorry, but